In this video, you'll get a good understanding of how we use the truth table to determine the validity of an argument. We'll also review the difference between a logically valid argument and a sound argument. First, remember when we're in logic, we talk about arguments, we're not talking about the pejorative sense of that, like yelling at each other, I'm right, no, I'm right. We're talking about trying to establish a conclusion. Now, the part in logic that helps us to establish that conclusion is having our argument be valid. You may remember from chapter 1 that the valid argument is one that is necessary truth preserving due to its form or structure. And by necessary truth preserving, we meant there's no way for the premises to be true and the conclusion be false. What we meant by securing that necessary truth preserving through its form or structure will become apparent as we go along. You may have worried, but how can I be sure that I thought of all the possible ways for the premises to be true to make sure that the conclusion can't be false? Maybe there's some way I just didn't think of? Well, the fact that we've done enough logic to get us our truth tables and to see how we can evaluate propositions with those truth tables means that we have the tools already to ensure that we account for every single possible variation in truth values. So the first thing we want to do is to translate our arguments from whatever natural language you're speaking, English, Spanish, French, into our language of propositional logic, or PL. Next, we use what we learned in 3.4 to make a joint truth table with the last proposition being our conclusion. And remember, from 3.3 and 3.4, the whole point of making these truth tables is that we're listing out every possible combination of truth values for those simple propositions that go into making up our complex propositions. The truth value of those simple propositions, combined with the different connectives that are found in our complex propositions, are going to determine the truth value of those complex propositions. So we will have accounted for, using this truth table method, every single possibility. So if we have a row that has true premises but a false conclusion, well, that's going to mean that our argument is invalid. But if we don't, well, since we've covered every single possibility, we know that this must be a valid argument. That proves to us that our argument is necessary truth preserving, that in all cases where the premises are all true, the conclusion also is true. Here's our first example from the chapter. If Maisie is a Kelpie, then Maisie is a dog. Maisie is a Kelpie, therefore Maisie is a dog. So we'll have K stand for Maisie is a Kelpie, D stand for Maisie is a dog. Here I've listed out all the possible combinations of truth values. So in the text, Smith notes that you don't have to repeat the columns K, D over there on the right-hand side because we have them in the key pretty much. Those are the premise and the conclusion, K and D, and I just have it repeated there. So you don't have to do that. I'm going to do that just to keep it straight for all of us slow folk like myself. Also, he notes that you don't have to put the truth values of K and D in that conditional section. You can just, look at the truth values of K and D over on the key over there on the side, and then fill in the conditional as it's supposed to be filled in according to its truth table. Again, I'm just for the sake of people like myself, I'm gonna go ahead and put them in anyway. So here are the values for K and the values for D. Looking at my conditional truth table, I know it's false only when the antecedent is true and the consequent is false. Otherwise it's true. Otherwise it's true. And there we go. Here is a representation of this argument. So now I have the truth value of the first premise, the truth values of the second premise, and the truth values of the conclusion. What I'm going to do is look for each row, see if I have any row where both of the premises are true, and if so, I'm going to check to see if the conclusion is false. If the conclusion is false, my argument is invalid. If there are no cases where that happens, then my argument is valid. So I look at this and it looks like first row, right? I have a true premise, and then the conclusion is true. So I'm okay there. Second row, I have a false premise. Don't even need to look any further. I don't care what the conclusion is on that second row. The fact that I have a false premise means that that's not going to count. And then for the bottom two rows, K is false in both of those. So both of those have a premise that is false. So really it's only row 1 where we have both premises true and the conclusion false. This is a valid argument. Here's a second example of an argument. It's not the case that Maisie is a Kelpie. If Maisie is a Kelpie, then Maisie is a dog. Therefore, it's not the case that Maisie is a dog. So Here's what it looks like. Let's go ahead and fill out our rows. The truth table for not, it tells me that I have to switch the T's and F's. The truth table for a conditional tells me that if I have a true antecedent and a false consequent, then I have a false conditional, otherwise it's true. So there you have it, the truth values for our different propositions. I'll go ahead now and check the different rows and see if I have any true premises, all true premises and false conclusion. Looks like the first two rows I have false premises. I'm not worried about those. The second two rows, the second pair of rows, I should say, I have true premises on both of those rows. So let's check and see the conclusion. Row number 3, I have a false conclusion. So even having one row, I mean, notice the bottom one, we have all truths. We're good on that bottom row. But even having one row where we have all true premises and a false conclusion makes it so that this is an invalid argument. Why? Because that tells us there's some possibility here that the things that we're claiming to be true, these premises, could be right, they could be correct, and yet the conclusion still be false. And one thing that's great about these truth tables is that they not only tell us that this argument is invalid, but they show us the counterexample to this structure of argument. In fact, we know all the different possible ways for this argument to go wrong. In this case, there's only one. But each truth value assignment to these simple propositions that make up the complex propositions that we're looking at, each one of those assignments that gives us true premises and a false conclusion shows us a case where our argument doesn't work. It's a counterexample. Now, normally when I hear that word counterexample, I hear it used as more in like the natural language type of argument. So for example, looking at the way this argument looks before we symbolize it out, before we translate it into propositional logic. If you tell me that Maisie is not a Kelpie, and if Maisie is a Kelpie, then she is a dog, therefore Maisie is not a dog, I'm going to tell you, well, if Maisie is a Boston Terrier, then she is a dog. Look, there's an example of how your premises can both be true and yet your conclusion be false. So usually that's the way we use the word counterexample. What's nice about these truth tables is it shows me exactly how my counterexample is going to be structured. I'm going to have to craft a counterexample where the fact that Maisie is a Kelpie is a false proposition, the fact that Maisie is a dog is a true proposition, and then I'll get my counterexample. So our propositional logic language shows us what the structure of the counterexample is going to look like, but it's not going to tell us what could be in those counterexamples. And in fact, one interesting thing here is there might not be a counterexample that I can point to say, hey, look, I know you argue this way, but there are some dogs that are not Kelpies. I might not be able to do that, but setting it up like this in this structure shows me, but I should be able to, right? There should be some counterexample somewhere, or at least a counterexample in theory. Okay, now let's go ahead and try 4.1.2 exercises where we'll practice this using truth tables in order to determine whether or not an argument is valid. Looking at the truth tables for my disjunction, it's only false when I have two false disjuncts. A conditional is only false when I have a true antecedent and a false consequent, otherwise it's true. Looking at my conclusion here, I have that in, hopefully you notice that the red outline, that's the conclusion there. But looking at my conclusion here, looks like I have to build in that inner conditional there, if B then C, and then I can build the second one. Same rule, antecedent true, consequent false, false conditional, otherwise true. And same thing for the outer conditional. Now, final step, we're going to go row by row and see any rows where we have true premises and a false conclusion. Remember, if we get one of those, then we're set. We know that it's invalid. If we look at every single one and we don't see one of those cases, then it's valid. First row looks like we have true premises and a true conclusion. Second row, we have a false premise, so I'm not worried about that. Third row looks like all truths. Fourth row, true, false, so I'm not worried about that one. Fifth row, all truths. Sixth row, all truths. And the seventh and eighth rows, I have false premises, so I'm not worried about that one. Looks like this is a valid argument. Now, let me see if I can make sense of this for you. Premise 1 says either A or B has got to be true, right? Premise 2 says if A is true, then C has got to be true. So let's pretend that A isn't true, though, and at least one of these is true, right? It's got to be B. Well, then in our conclusion, we say Well, if it's the case that if B is true, then C is going to be true, then C would be true, right? And sure enough, like if it's either A or B, then yeah, if A is going to give you C, then in the conclusion here we have if B is going to give you C, then you're going to have C. Number two, we only have one premise here, and it's just a negation. Negation makes me flip the T's and F's. In our conclusion, I'm going to have to build those two conditionals on the inside of that conjunction. And remember, conditional is only false when the antecedent is true and the consequent is false. Now I build that conjunction, only true when both conjuncts are true, otherwise it's false. Now I have to negate that conjunction. And finally, I have a disjunction, which consists of the negation of that big conjunction and also the proposition C. Remember, a disjunction is only false when both disjuncts are false, otherwise it's true. Now, it looks like I forgot to delete my row of A in the premise. So now let's look at all of these rows. Again, I'm only looking for rows where the premises are true, and then I'm going to check and see if the conclusion is false. I only have one premise here, which is not A, and not A is only true in the bottom 4 rows. And when I look at those bottom 4 rows, it looks like the last row, the premise is true and the conclusion is false. Therefore, this is an invalid argument. Problem 3. Problem 3 says that if it's the case that A and not B are both true, then C is true. But C is not the case. B is also true, therefore A cannot be true. So let's see. In that first premise, I'm going to have to build first the negation of that B. Then I'll build the conjunction in that antecedent. Remember, only true when both conjuncts are true. Now I'll build the conditional. Only false when we have a true antecedent, false consequent. And now I'm going to work on premise 2. All I have to do is the negation there, flipping the T's and F's. And I also have to do the negation for the conclusion too. All right, now I check my rows. I'm only looking for rows with all true premises. Then I'll check to see if there is a false conclusion. Row 1, I have a false premise. Don't worry about that. Row 2, all true premises, false conclusion, invalid argument. Problem 4 says A and B are true if and only if C is true. A is true, and then the conclusion says if C, then B. In premise 1, it looks like I'm going to have to build the conjunction first, then I'll work on the biconditional. Conjunction, only true when both conjuncts are true. Biconditional, only true when both components are true or both components are false, otherwise it's false. And finally, I'll do that conditional in the conclusion, only false when we have a true antecedent and a false consequent. Now I'll check my rows. Looks like row 1 has true premises but a true conclusion. Okay. The next row that has true premises, all true premises, is row 4, and that has a true conclusion. Good. And then we don't have any other rows with all true premises. Looks like this is a valid argument. Problem 5 says both it's not the case that A and it's not the case that B, if and only if it's not the case that C, but it's not the case that either A or B. Therefore, if it's the case that C, then it's not the case that C. I can tell you right off the bat, that doesn't make any sense. That C couldn't be true in this case, because then that would make not C true, and in our propositional logic, that is not possible. We're not allowed to do that. But that conclusion doesn't say that if not C is true, then C must be true. So we're still okay here. It's just going to be the case that C will always be false. First, I'm going to work on negations for single propositions or simple propositions. So that's flipping the F's and T's. Next, I'm going to build a conjunction in the biconditional of premise 1. Remember, conjunction only true when both conjuncts are true. Now the biconditional in premise 1, remember true when either both components are true or both components are false, otherwise it's false. Now in premise 2, I'll build the disjunction. Remember, only false when both disjuncts are false. Now I'll negate that disjunction. Finally, I'll do the conditional in the conclusion. Remember, only false when antecedent is true, consequent is false, otherwise true. Now let's check our rows to see if there are any rows where we have all true premises. It looks like all the first 7 rows do not. Only the last row has true premises, and it also has a true conclusion, so this is valid. Problem 6 has premise 1 is A or B. Premise 2, it's either not the case that A or C. Premise 3, if B is true, then C. Therefore, the conclusion is C. Given that first premise, either A or B is true, or at least one of those two is true. If A is true, then the second premise says not A or C is true. Well, not A is going to be false, so C will be true. And if B is true instead on premise 1, then premise 3 says if B, then C. So either way, if A is true or B is true, C is going to be true. And premise 1 says one of those two is going to hold. So this one should be a valid argument. Let's see. I'll build first the disjunction in premise 1. Remember, only false when both disjuncts are false, otherwise true. Now the negation in premise 2. And then the disjunction, only looking for when both disjuncts are false, otherwise it's true. The conditional in premise 3, only false when the antecedent is true and the consequent is false, otherwise true. Okay, so row 1, I have all true premises, true conclusion, I'm okay there. Row 2, I have a false premise. Row 3, all true and a true conclusion. Row 4, false premise. Row 5, all premises true and a true conclusion. Row 6, false premise. 7 and 8, false premises, valid argument. Problem 7, it's not the case that either A or B, if and only if it's not the case that C. Premise 2, it's not the case that A, and it's also not the case that B. Therefore, it's both the case that C and it's the case that not C. Now, I can tell you right now that conclusion will never be true. That's always going to be false because that's a contradiction. And in our propositional logic, we have sort of have built into the system that that's always going to turn out a false. So if there are any cases here where the premises are going to be true, then this is going to be an invalid argument. One interesting thing, and I haven't done this yet, but if the premises are never all true in any of these rows, this will turn out to be a valid argument because you won't have any case where the premises are true and the conclusion is false. So you may worry like, well, does that mean like we're proving something that's contradictory? Isn't that a problem? Not a problem. Even if it's a valid argument, the premises will never all be true, so you're never going to get this conclusion. So let's go ahead and fill in our premises here. First, I'm going to start off just negating simple propositions. Remember, just flipping F's and T's. Now I'll build the disjunction in that biconditional in premise 1. Remember, only false when both disjuncts are false, otherwise true. Then I'll negate that. And then I'll do the biconditional true when either both propositions that make it up are false or both of them are true, otherwise false. Now the conjunction in premise 2, only true when both conjuncts are true, otherwise false. Finally, the conjunction in the conclusion, only true when both conjuncts are true, but like I said, you're never gonna get both of those things true, so it's always gonna be false. So we don't even need to check the conclusion. If there are any cases where the premises are both true, then we're gonna have an invalid argument, and I sure see row 8, we have true premises, so invalid. Argument 8 says, if it's not the case that both A and B, then it is the case that either C or A is true. Premise 2, either it's not the case that A or it's not the case that B. And that's actually the antecedent of premise one. It's not the case that both of those two things are true, A and B. That means one of them's got to be false. At least one of them's got to be, possibly both of them's false. And that's what premise two says. So C or A is going to end up being true. Premise three says that A is true. Now, if C or A is true, remember that just means that at least one of those things are true. So if A is true, that doesn't mean that C is false. So I actually would expect to see as a conclusion not C, and that would be an invalid argument. But actually the conclusion says it's not the case that either C is true or not C is true. I know that that conclusion is going to be false all the way down. That is a violation of the law of excluded middle, that you got to be one or the other. You have to be true or false. And again, we have that sort of built into our system here where the law of excluded middle always holds. So that conclusion is always going to be false. If the premises are ever all true, then we're going to have an invalid argument. Okay, first I'm going to do those simple proposition negations, get those out of the way. Remember, just flipping F's and T's. Next, I'll build the conjunction in the first conditional there. Remember, true only when both conjuncts are true. Then I'll negate that. I'll build the disjunction in that consequent. Remember, only false when both disjuncts are false. And now let's build that conditional. Only false when we have a true antecedent and a false consequent, otherwise true. Premise two, we can build that disjunction pretty easily. Only false when both disjuncts are false. Premise three is a simple proposition. We don't have to build that at all. Let's build the disjunction in the conclusion. And just like we thought there, C or not C, one of those, either C or not C, is going to always have to be true. So that's always got to be true. Now we're negating that. So we're negating all those trues. They're all going to be falses. And now we look for all true premises. Looks like row 3, 4, 5 have, row 3 and 4 have all true premises and a false conclusion. Sure enough, invalid. Problem 9 says, if A is true, then both of these guys are going to be true, both B and C. But premise 2 tells me that can't be the case. You can't have them both true, right? If B is true, it's going to make C false. So this B and C can't be true. But if A were true, then this would be true, so A can't be true either. And that's what our conclusion is. This looks like a valid argument, but let's see. First, let's negate simple propositions. I just like to get those out of the way first. Otherwise, I usually like to go in order. All right, for premise 1, we'll build the conjunction first because it's inside of the conditional. Only true when both conjuncts are true. Then the conditional, only false when we have a true antecedent and a false consequent. Then we'll do the biconditional in premise 2, true when both components are true or false. Otherwise, it's false. Finally, we'll check our rows. Looks like rows 6 and 7 have true premises and both have true conclusions. Valid argument. Problem 10 says, if A then B, if B then C. It's not the case at C, so it's not the case at A. This is going to be a valid argument, because think about it. If A is true, that's going to make B true in premise 1. So now we have B is true, then C is going to be true in premise 2, but premise 3 says C can't be true. Well, then A couldn't have been true in the first place, so A's got to be false. But let's check it out. First, I'm going to negate those simple premises, and I just do that because I like to get it out of the way. Otherwise, I usually go in order. Next, we'll work on the conditionals. Only false when we have a true antecedent and a false consequent. Now we'll check for all trues. Looks like that happens in last row, row 8, but we have a true conclusion, valid argument. It's kind of weird for us to go from exercises to back to talking a little bit about this stuff, but one last little section here. It's kind of important for us to understand what it is we just learned or what that shows. One temptation is to think that if we've shown that an argument is valid, we've also shown that the conclusion is true. So consider, for example, this argument, snow is white and grass is green. Well, are there any places where the premises are true and the conclusion is false? No. But does that prove our conclusion? We might be tempted to say yes, but that's probably because we already know that snow is white and grass is green. If I switch that around to being snow is white and grass is gray, now we know that the G is false. But notice we have the same structure here, right? It's still the case that we never have true premises and a false conclusion. What's going on here? How is this a valid argument structure, and yet I have this weird case where the conclusion is not true? Well, remember that all we're showing by validity is if you have true premises, then you have to have a true conclusion. We're not saying that you do have true premises. We're not saying which row it is that you're on, the row with all true premises or a row with false premises. Determining which row you're on, that's a matter of empirical investigation of the world, seeing how the world is. Is it the case that snow is white and grass is green? But if it's the case that we do that empirical investigation and we know that we have true premises, and it's also the case that we have a valid argument like this, then we know that the conclusion is also going to be true. That will be a sound argument. So what we've achieved in logic is a valid argument. We now need to do the work of seeing whether those premises are true, and then we'll get a sound one, and then we'll know that our conclusion is true. That's all for this one. Go ahead for the next time, please read 4.2 single propositions and do the exercise 4.2.1.